Today we're going to be talking about volume of prisms and cylinders. So let's think about it. If solids have the same height and matching areas everywhere along that height, then they have the same volume. We can look at a stack of playing cards, and it doesn't matter if it's all neat and inside the box or if we fan it out. Same for a stack of coins. If we took that stack of coins and made them as neat as we can, or we pushed it a little bit so that they were leaning, they would still have the same volume. This is called Cavalieri's principle. Bonaventure Cavalieri came up with this, and it basically states that if two prisms have the property that all corresponding cross sections have the same area, then those prisms have the same volume. Volume of any prism equals area of the base times the height. Well, I'm going to use an uppercase B to represent the area of the base times the height. Let's look at this hexagonal prism. If we have here the area of the base is 3 times the height of 4, I'm going to get 12. And because volume is the number of cubic units, it's 12 cubic units. This is an oblique prism. It's that same prism, we've kind of tipped it over. Well, the bases are still parallel, but they're not directly over one another. That's what an oblique prism is. Okay? If they have the same height and matching areas, they still have the same volume. So we have 12 cubic units. Let's look at this oblique pentagonal prism. Again, we have the area of the base is 3.5, the height is 6. We're going to have 21 cubic units. Now you can add volumes together as long as they do not overlap. Well, if you look at this picture, the outside overlaps, but not the volumes. What overlapping volumes would mean that it was inside of one another. All right, so let's talk about similar figures and how area and volume affect those similar figures. So we have this blue prism and a red prism. If we're going to find the scale factor first, 2 to 3, 6 to 9, and 10 to 15. Now if I take each one of those, it reduces to 2/3. Therefore my scale factor is 2/3. Now in order to compare the area, I need to find the surface area of each prism. That is the perimeter of the base times the height plus 2 times the area of the base. Now, the blue, the perimeter of the base is 24, the height is 6, the area of the base is 20. For the red, the perimeter of the base is 36, the height is 9, and the area of the base is 45. I always want to identify those before I start plugging them into my formulas. So the surface area of the blue is 24 times 6 plus 20 times 2, and the surface area of the blue is 184. Now that's going to be in square units because I'm finding area. Of the red, I have 36 times 9 plus 45 times 2. The surface area of the red is 414 square units. Now if I set it up as a ratio from blue to red, I get 184 over 14, which reduces to 4/9. So my area ratio is 4/9. Now let's talk about volume. Volume is basically this. Remember, area of the base times the height. So the area of the base for the blue is 2 times 10, which is 20, times the height of 6, which is 120 cubic units. Of the red, I have 3 times 15, which is 45, times 9 is 405 cubic units. So the ratio of the volume ratio is 120 over 405, which reduces to 8 over 27. All right, so let's talk about the scale factor, the area ratio, and the volume ratio. If I look at them, the scale factor was 2/3 and the area ratio is 4/9. The volume ratio is 8 over 27. I'm looking for something that I can compare it to. Well, I know that area is square units. Well, 2 squared is 4. 3 squared is 9. Volume I know is cubic units. 2, my scale factor, 2 cubed is 8, and 3 cubed is 27. Therefore, if the scale factor is A over B, then the area ratio is A squared over B squared. Makes sense? Okay, so what do you think the volume ratio is going to be? Yep, the volume ratio is going to be A cubed over B cubed. And that's going to work for any time I have area or volume of a prism or cylinder.